Hello, I want to thank you for joining me with part two of Case for the Continuum Hypothesis. And I'm going to lay out the axiom that I believe will affirm CH. And most of you who are mathematicians will probably disagree with it, in which case you can do a ponage video. You can comment right there on the screen there to say, well, this is ridiculous, and I will put it on there, but it's moderated, so, no personal attacks. You start calling me names, and people have done so before, it's just not going to be put up there. So, but you can cite anything in the literature to prove me wrong, and I welcome it. I welcome free and open debate. And at the very, very end of this series, I'm going to tell you a little bit about who I am and what my personal story is, and but that's going to be at the very, very end of this video series. Meanwhile, there is no me. There's just the idea that we're talking about here. The central axiom that I believe added to set theory will affirm CH, okay? Because as it is, according to set theory, the continuum hypothesis is undecidable. Don't argue with that, all right? But this axiom, I believe, is consistent with set theory. I believe it's consistent with the axiom of infinity, and I'm going to make a case for that. And I believe that standing with set theory will affirm CH, okay? Here is the axiom, as incredible as it sounds, and that is that if I take any set above Aleph Nought, okay, Aleph 1, Aleph 2, Aleph 3, Aleph 4, and I say, okay, I take the null set of that set, that is impossible. That you cannot have the null set of any set above Aleph Nought and have it mean anything. Now, the null set of Aleph Nought would be the null set. In other words, 0 times Aleph Nought is equal to 0. But the null set of any number that we would say would be a greater cardinality than Aleph Nought, to use the term cardinality, I'll use that term because there's no choice, that's the language, would not exist, would not be possible, would be impossible given the nature of what those higher levels of cardinality are. They are not based on the 0-1 dichotomy, a kind of the counting numbers. If you look at the axiom of infinity, you are generating the counting numbers based really on a 0-1 biconditional here. Now, that's an incredible statement, but let's start off with the null set. And I ask the question, how many sets are in the null set one way? Okay, looking at it from one standpoint, well, the null set means no set. Okay, so there are 0 sets in the null set. But if I look at it another way, I say, well, wait a second, I've called something the null set. That is something I've now made discrete. I've now made that there is a set called the null set that is there. How many members are in that set? 1. Well, the null set. So it's the same question tweaked a different way. Depending on how you ask it, you either get 0 or 1. Well, with the axiom of infinity, you're generating, you're taking that 0, 1, and now you're generating, well, how many members is in the set 0 and 1? 2. Okay, how many members is in the set 0, 1, and 2? 3. And you go all the way on up until you get to Aleph Nought. Now, at each and every step of the way, though, you're still beginning, that recursion, that primitive recursion begins with that central question. It's almost like the primal question. We're leaving negative numbers aside here, okay, because that's further along. We're just looking at very primitive set theory-based arguments here. You're looking at the same question, how many members is in the null set, 2 different ways, okay? I either have a way that arrives at 0 or I have a way that arrives at 1. In some sense, 2, 3, 4, 5, 6, 7, 8, 9, 10 would be a way of beginning with that dichotomy and then generating further numbers using, once I get 2 members of a set, I can build up. But if you really want to think about it, I can generate any number using binary. Those of you who are computer people know what I'm talking about. I can use 0, 1, 0, 1 to define a number. I either have something in a certain decimal place or I don't. And so that's base 2, where I either have 0, 1. Any base above that just generates the same number. So in some sense, my 1 can then become a 1 or a 2. If I were to have a decimal system based on base 10, I don't have any more numbers than I would have just on base 1, 0, or base 2. All right. That's a little far afield, so I'm not going to dwell on that. You understand the basic point here, that a discrete counting system, if I took anything based on discrete numbers, whether they're natural numbers or rational numbers, where even though if I have one rational number and then the next rational number above it, that's an infinitesimal distance, still conceptually we can say there's a discrete distance there, even if it's infinitesimal. If I took all the rational numbers between 0 and 1, I can in some sense say that they're countable, the way that Cantor proved. Okay, they can correspond to the countability. There's no, if I took all the rational numbers in existence, I wouldn't have any more numbers than I would with integers. Okay, so what about levels of infinity above Aleph Nought? Well, if I were to take the example of all the real numbers between 0 and 1, there would be more of them than there would be our counting numbers. Cantor proved that too. Okay, so the bottom line is, in what sense would I say the real number and then the next real number above that? Even saying that that's discrete or infinitesimal is paradoxical, because what I'm actually dealing with is something smooth, or a continuum. If I take 0 and then say, well, ask myself, what's the next real number above 0? I have a paradox. Okay, because 0 flows into the non-zero finite realm there almost like it's a smooth thing. I know quantum physics is overused with the particle-wave dichotomy thing, where, you could argue that if you look at it as rational numbers that are like particles, and you look at it as the continuum, it's like a wave. Okay, you're ready to punch my face off for putting it that way. I know quantum physics is overused, but I kind of like the metaphor. It's fun. Okay, even if it's not something so literal. So, in what sense, if I have a set Aleph 1, yeah, in what sense is it actually a discrete thing that we would call a set? Where I either have Aleph 1 or I don't. If I have Aleph 1, is that based on the 0-1 dichotomy? Think about it now, okay? If I have Aleph 1 numbers between 0 and 1, they're going to transcend that amount of numbers are going to transcend the counting numbers. So that will not be a discrete, this number, this number, this number, this number, this number, if you think about it. So you cannot generate them using the axiom of, you cannot generate Aleph 1 using the axiom of infinity, using the simple 0-1 dichotomy. Yeah, we say it's a set, and we say Aleph 1 is cardinal, but Aleph 1 really transcends anything we would call cardinal. So in some sense, the minute I make Aleph 1, let's say the minute I make Aleph 1 a cardinal, and I have 0, and I ask myself, okay, how many Aleph 1s are in Aleph 1? I have a paradox, because the minute I say 1, I'm treating Aleph 1 as almost like Aleph Nought. Okay, I'm treating it as substantially no different. Now, you might argue that Aleph 1 is some other level of discreteness than Aleph Nought. We just haven't discovered it yet. If that's your argument, that's an interesting one, in which case you won't accept the continuum hypothesis, because you'll accept some kind of discreteness between discrete and smooth. I think that whole idea is paradoxical, that you could have discreteness between that isn't discrete. I mean, that I would say that once you've left the realm of something being defined by discreteness, it's not discrete any longer. Okay, and so the idea of 0 times a number being 0 only makes sense if you're operating from the 0-1 dichotomy, where I either have that number, in which case that's 1 times that number, or I don't have that number, in which case I take the set away, in which case there's no set, you have 0. Okay, so 1 times 4 equals 4. Well, I have 4 here. Let's say I have 4 balls, and then I take the 4 balls away, I have 0. But I don't, if in the case of Aleph 1 balls, I wouldn't have a discrete set of balls. So in some sense, there is no taking those away. There's no I either have it or I don't. The whole dualism has been transcended here. And so I believe that axiom is consistent with the axiom of infinity, and that's what I'm going to use. Thank you.